Hello there, welcome back to another video lesson. Today we're going to be talking about the van der Waals equation of state. And van der Waals equation of state is going to be used for situations where we're not at ideal pressures and temperatures. So we can see that this equation is similar to the ideal gas law, except for it has a few changes. It has this B value and this A value, and so this B value accounts for the amount of space that the molecules take up. So that's the actual volume of the molecules in the situation. And then this A is the it's an accountability factor for the forces going on in the situation between the molecules. And you might notice that we don't have the number of moles here, and that's because we just simplified the situation and made this volume not just any volume, it's the volume, it's the molecular volume. So that means it's the volume of the molecules, like the volume of 1 mole of molecules for this situation. So the graph-wise, like graphically for this on a pressure versus volume graph, you're going to have your values, and they're going to start out at an ideal gas where they're going like this, but eventually they're going to start to kind of have inflection points, and they're going to increasingly kind of get these inflection points. It's a very poor graph here, but it gets the idea through. And it has these inflection points where at what we're going to call these critical points. So at the critical temperature, critical pressure, and the critical volume. And so at these inflection points, the first and second derivatives are going to be equal to 0 here. And so what this is going to allow us to do is manipulate these equations and find out our values for A and B. Really powerful here. So I'm going to go ahead and take the first derivative and the second derivative. So we've got RT over squared plus 2A over volume cubed. And then we're going to go ahead and take the second derivative of this, and that is going to be equal to 2RT over B minus B cubed minus 6A B to the fourth, but then this 2 and the 6 will cancel to make that a 3. Okay, so now we're going to go ahead and plug in our temperature, pressure, and volumes at their critical points, at these inflection points, so we can set them equal to 0. So if we set them equal to 0, we end up with the 2A over critical volume cubed is equal to RT, critical temperature, over critical volume, ooh, that's not a C, minus B squared for the first derivative, and then for the second derivative we're going to end up with we're going to have RT over B minus B C and C cubed, and we're going to have that equal to 3A over BC to the fourth power. And we want to solve for B first, and we notice that if we take the reciprocal of this second derivative and multiply it by the first derivative, that'll allow us to do some good simplification here. So I'm going to go ahead and do that. So we're going to end up with 2A times critical volume of fourth over 3a times critical volume to the third. And so that'll simplify out the a's, and then this will cancel, and we'll just end up with 2/3 VC. And we're going to set that equal to the R times TC times the critical volume minus B cubed over the RTC times the critical volume minus B squared. And so these will cancel out, and then so will that. So then I'm going to go ahead and rewrite it, and we end up with 2/3 BC is equal to BC minus B. And so to go ahead and solve for B, we end up with B equal to 1/3 BC, or V over VC over 3. Alright, so now that we solved for B, we can just go ahead and plug it back into this first derivative here and solve for A pretty easily. So we're going to go ahead and get 2A over BC cubed, set that equal to R, critical temperature, and then the critical volume minus the critical volume over 3, and all of that is squared. And so this is going to end up being 2A, the side doesn't change, and then we also get, going to go ahead and simplify that, so that's just 2/3, and then that's squared, so we get 4/9 BC squared. And so that's going to be 2A over BC cubed is equal to 9 over 4 RTC BC squared. Alright. So now that we did that, I'm going to go ahead and solve for A. So I'm going to move this all the way over here. I'm going to be working left to right. So we are going to have 2A equal to 9 times RTC times BC cubed over 4 BC squared. And then I'm just going to go ahead and divide by 2. So then we're going to have A is equal to 9/8 BC squared RTC times BC cubed. And then we're going to go ahead and simplify this here. And A is going to be 9/8 times RTC times the critical volume. Alright, so now that we've solved for A and B, that's pretty important. We were able to just manipulate these equations, and now we have the values of A and B in terms of just the critical temperatures and volumes. So now that we know A and B, we can go ahead and plug it into the van der Waals equation state with our critical values. So we've got R times TC over, got the minus B, and since we now know B, we got B squared minus, and then our A value, 9/8 times the gas constant times critical temperature times the critical volume over critical volume squared. So this will cancel, we'll end up with that, and then we notice that this here is going to just be 2/3, end up being 2/3 BC. And I think I made a mistake. Yeah, this is not squared. I was pulling that from the derivative. That is not squared. So we just end up with 2/3 VC from this value here. So we see that blanking. Our critical pressure is equal to RTC over VC times 2/3 minus, because we canceled these, we got that, minus 9/8. And the 9/8, that's gonna, or the 2/3 minus 9/8 is going to simplify to 3/8. Yeah, 3/8. So we now have that equation. And so if we just go ahead and rearrange this to set them equal to each other, so we're going to end up with 3/8 is equal to PCVC over RTC. And so this right here, oh, that was really poorly drawn. So this here is commonly referred to as Z. That's just the letter they picked, and that's the compressibility factor of a non-ideal gas. And so this Z is really important because in real practice, it's extremely difficult to like experimentally find the critical volume. It's easier to find the critical pressure and critical temperature experimentally. So when we use Z, it's often that we know the pressure and the temperature at the critical points. So it's kind of like a pseudo way to solve for the critical volume. And since we don't typically know the volume, and we can find it, so let's just go ahead and do that. So I'm going to go ahead and solve for VC. So we've got the VC equals to 3/8 times, how's this going to work out here? We're going to have to flip it. So RTC over P, the critical pressure. All right. And so now that we've solved for VC, we can go ahead and just plug it into values. So I could plug it into A and B if I wanted to. So I'm going to go ahead and just do A first. So now we're going to have A equal to 9/8 times RTC times the volume, or critical volume, which is now 3/8 times RTC over PC. Alright, so now if we go ahead, we can pull, go ahead and do some simplifying. So we've got 27 over 64 times R squared T squared over the, that's critical temperature, over the critical pressure. And I'm going to go ahead and do B as well. So B is equal to just VC over 3. So we have VC is equal to 3/8 times the gas constant, critical temperature, critical pressure, all divided by 3. So simplifying it, 3's cancel, so B is equal to RTC over 8PC. And so since we found these A and B values without the critical volume in it, we can go ahead and just calculate so many experimental values for any compound. Like, it doesn't, the possibilities are endless as long as it's not at ideal temperatures. So we can now do ideal and non-ideal situations, which is extremely powerful. I hope you enjoyed the video, and thanks for watching.